Okay, hello everyone and welcome back to your YouTube channel. And welcome to this very exciting and interesting video today. And probably it will be extremely helpful for some of you. I am recording this video because I am involved in this course that is called Power System Operation and Smart Grid. And one of the subjects inside this course, specifically to the area of power system operation, is related to economic dispatch. Everybody that knows me understand that I find boring the steady-state analysis of the power system. However, what I can tell you is that I am creating this video in order that my students can see how exciting the economics dispatch can be when you consider the mathematics, the numbers behind the physical concepts. And today, this is a very simple, a very fast video, very quick video, that is presenting a very short introduction about, let's say, optimization problems in power systems. And then I will jump into one very specific example about economic dispatch. But before I start, I would like to recognize that this specific document was created by my teaching assistant, and he is a very clever guy that he is doing quite well with the teaching assistant activity. His name is Liham, and he is working extremely hard. That I was surprised. I was not planning to record any video about economic dispatch, but when you have somebody that is giving you a lot and producing, I feel that is my responsibility making clear his contribution, but also he pushed me to do something bigger and better, and that is what I love working with extremely clever people, okay? Well, without further delays, let's do the following. I will jump into the document prepared by Linam, and from there I will run a very short explanation, okay? Before you send me an email and request for the document, I am afraid that the document is not ready for public disclosure, okay? Only my master students will have access at the moment of this document, and hopefully in I don't know how many months or years we will have this document publicly available, okay? Well, let me start with a very short introduction, okay? I not consider myself an expert in power system economics. However, for me, it's something fun that I can explain to my students the problem of operation of power system using more mathematical understanding and physical understanding, okay? What you need to understand is that traditionally we solve the problem of load flow. And when we solve the problem of load flow, what we are trying to obtain is the balance between generation and demand. However, inside the electrical power system, there are several control systems, and those control systems, they have specific functions. And those functions are related with specific control variables. Those control variables can be or must be optimized in order to ensure the optimal operation of the electrical power system. And that is where many of the problems inside the electrical power systems related with those control loops are solved using mathematical tools, mathematical techniques, optimization, okay? Many of you know that there is a very slow control for frequency control that is called the automatic generation control, the AGC. The AGC is a very simple controller, okay? There are 1,000 papers using very complex mathematics and so on, but the majority of the real implementations, they use just a proportional and integral controller, a PI controller, in order to minimize the control error, the area control error, that is also called ACA. And to minimize that error, control area error, we include some constraints. It's an optimization problem when we can include some constraints related with the machines and the system dynamics, okay? This problem related to the AGC is basically a problem that can be solved in a time scale that is relative small for power system optimization in terms of seconds, okay? Then we have a very powerful tool that we use to minimize the instantaneous cost of operation, some other index, okay? For instance, that tool is called the optimal power flow. Optimal power flow, or OPF, is basically a tool that we use to minimize this cost of operation. And more recently, we start to include some other indicators like pollution, CO2 emissions, and so on. However, again, this problem is typically in a time scale, a time horizon of minutes. Then we have a relative longer time horizon, probably hours, depending of the market, depending on the intention, but we are trying to minimize the expected cost of operation and some other indicators, and that is the classical unit commitment. The classical unit commitment is basically try to reduce the cost of operation. However, there are some variations. More recently, we have started to include some other constraints inside the optimization problem, like security, but also in this time frame, we can talk about the hydrothermal coordination, okay? And then we have the minimize the cost of operation and other indexes, but for a longer time periods, days or weeks. In this case, we call this problem the hydrothermal coordination, okay? How we can explode, how can we use different energy resources, but at the same time, we understand that those resources, some of them, they have a different cost, but also they are renewables or not renewable, and we need to include that into the cost, the economic operation of the electrical power system. The two other problems that we have here, time scale, time horizon of months, and it's basically minimizing the operational cost. But in this case, we care a lot about reliability index, reliability indicators, and we include that as constraint inside this problem, okay? When we are solving this optimization problem of minimizing cost, but including reliability constraint in the scales of months, we are basically concerned about the maintenance and the interchange scheduling in the electrical power system operation. Finally, the longest or the longer time scale, time horizon is years. And in that problem, what we want to do is maintenance schedule and generation planning, but at a time scale that is very long, years. And the idea is that we want to minimize the investment cost, probably deferring the installation of some transmission lines, transformer or generator. But every time that we modify the maintenance and the planning, generation planning, we are affecting the operational cost and also the reliability. For that reason, there are many power engineers in the planning area that they are dedicated to this kind of static studies, optimization problems in order to see what will happen in the future and to define possible solutions considering minimizing the operational costs and of course ensuring the proper reliability for our customers, okay? Well, this document is amazing. Lee Nam has made an amazing job. I pushed him to include more mathematics, and he started talking here the cost of operation, and so on, then establish the constraints, equality constraints. And he did a very good job with the mathematics. I like it. And also I asked him to include some step-by-step solution. I will not cover this here. He will be doing something like this in classes, but I want to go to one very specific problem. In this exercise, question number 4, I stop here because as Lee Nam has been doing a very good job, he's pushing me, and we want to push the boundaries, okay? That is what we love. And the idea is that here in this document, in this piece of paper, if you print it, basically we are presenting the step-by-step solution with a lot of comments, okay? I know that these kind of problems are solved in many famous books, Good and Wallenberg, Weedy, many interesting books, okay? However, the job here is, first we want to show the students how to do it in a proper way using mathematics, and then we will move to a couple of practical ways to solve this problem using another simulation or calculation software. And that is when that is the place where Lee Nam pushed me, okay? He produced this document, and I say to him, okay, let's try to do it with a couple software and see if we can match and demonstrate to people that you can do it by paper, but also you can do using the software, okay? Well, in this very specific problem, this is a very basic problem. Basically, is economic dispatch problem with a single equality constraint, okay? What we are doing here is basically we consider a very small system, simplified system, and we have 2 generation units, okay? Let's say this is generator G1 and this is generator G2. And those generators, we can assume that this is a simplified power system and there are no transmission losses, okay? What we have is there is a power load over here, and as you can see in the statement is 10 megawatts, okay? What is the idea? The idea is that we want to solve the problem. We want to solve the problem about the active power production of this generator 1 and this generator 2 in order to fulfill the responsibility and supply a reliable electricity to the load. However, in this problem, we are interested on the economic point of view. For that reason, if you look here, I say the cost of generation is given by these 2 equations, okay? The cost of generation on the generation unit 1 is 0.5 plus the power dispatch of that generator plus the square value of that dispatch. We have here again another cost function. This cost function is for the generator number 2, and you must be aware of the following. PG1 and PG2 represent the active power dispatch, and this cost function CG1 and CG2, both of them, they are in monetary units per hour, okay? What I'm telling you is if we put here inside this equation megawatts, well, the unit for this cost will be the cost in unitary units per hour, okay? Now, the question here is calculate the optimum values of the active power dispatch of the generators. In other words, we want PG1 and PG2 such that the dispatch satisfy the total demand. That means that the sum of those dispatches, individual dispatches, must be equal to the total load. For simplicity, and this is a very simplified, but it's an academic problem that we can solve by hand, assume generation unit have no technical limits, okay? This is not realistic. All of you know that every single generation unit, there are limits over there, but we will assume that here we don't have it, okay? The first thing that you must understand is that from the mathematical point of view, from the control point of view, we want to identify two control variables. In this case, we can use the letter x1, the variable x1 and x2 to define the thing. But to be honest, in power system, I prefer to use a more, let's say, physical-oriented variables. PG1 and PG2, they are the control variables, okay? And the requirement from the statement is that the total power dispatched by the generators must be equal to the load. In mathematics, and it's basically PG1 plus PG2 equal to 10, but in physics, in electrical engineering, that means that the dispatch of the generator 1 plus the dispatch of the generator 2 must be equal to the demand. In this case, 10 megawatts, okay? We can reorder this equation, and what we can do is move the 10 megawatts to the left, and we obtain the equation E1, okay? Now, we need to have a look on the cost function, because here at the very beginning, we give you the two-cost function, but the total cost function is the combination of the cost function of the generator 1 plus the generator 2. What I'm telling you is that this equation number 1 is the generic equation for n generators, but in this very specific case, we have two generators n equal to. As a consequence, well, the total cost is the sum of the individual cost. Then we put here the individual cost of the generator 1, the individual cost of generator 2, we combine. And beautiful here, I'm sorry, we have here the equation that we are looking for, and that equation is basically the equation that we are looking, is here, is the combined cost, generation cost of this system, okay? Okay, we are here, yes. What I'm telling you is that this is the cost of the generator 1 and this is the cost of generator 2. Perhaps I will stop using this, okay? Let me clean and let me move forward. Okay, this is the total cost, generation cost. Now we need to define the inequality constraint. The inequality constraint, the mathematics say that is a set of m equations. In this very specific case, m, the letter m for Mike, m is equal to 1 because we have a single equality constraint. In this case, the equality constraint is basically the power balance. That means the active power generation of the generator 1 and generator 2 minus 10 should be equal to 0, okay? Now, how do we solve this optimization problem? Well, many books show you several methods. In this case, we will use the Lagrange method, basically using the Lagrange function, okay? We define the Lagrange function. We use this letter over here, L, to represent the Lagrange function. And here we have the Greek letter lambda, and that lambda is used to represent in mathematics the Lagrange coefficient, or in electrical power system, specifically power system economics, that represent what we know as incremental cost, okay? Well, this equation number 9 is the equation, the general equation, but to be honest, in our case, we have generator 1, then we have here generator 2, and then we have lambda multiplying the equality constraint, and that is very simple, okay? What we did here is substituting the appropriate values. You can see the very beginning, the cost of generator 1, the cost of generator 2, plus, this should be a plus, okay? This should be a plus, and this plus lambda multiplying the equality constraint, okay? There is a typo here. Okay. Now we use the necessity optimal condition, that is basically calculating the derivative of the Lagrange function in terms of the control variables and equalizing that equation to 0, but also differentiating the Lagrange equation in terms of lambda and equalizing to 0. The job is to obtain the values of PG1, PG2, and lambda that makes those derivatives equal to 0. And you can see here, I expand here the situation, and you can see it's very simple. We expand the equation, and from there it's very simple. I will calculate only the first term, and that is the derivative of the Lagrange function, the Lagrange function in terms of PG1. This derivative is 0, this derivative is 1, this is 2 PG1, this is 0, 0, 0, 0, 0 respect to PG1, and as a consequence we get here 1 plus 2 PG1 plus lambda multiplying PG1, okay? Now the situation is we can do the same for the other two terms of the condition, and if we do that for the other two terms, well, the situation is that we arrive to a set of 3 algebraic equations where PG1, PG2, and lambda, they are the unknown variables, okay? To be honest, this is a set of linear equations. To be honest, we are happy that this is a very specific case where the Lagrange function creates 3 linear equations that we can solve. From equation 1, we can extract the generation dispatch generation for the generator 1. From the second equation, we can extract the active power dispatch of generator 2. And as you can see, this dispatch is in terms of lambda. But there is a third equation that is helping me a lot. Because if I put this equation and this equation in terms of the dispatch, well, I can do a very interesting mathematical trick over here. Because if I sum those terms, the sum of PG1 plus PG2 is equal to 10, and 10 is the 10 megawatts or the total load of the system. And when we do that, we arrive to this beautiful equation over here. In this equation, PG1 and PG2 disappear, and the only unknown variable is basically lambda. We can extract lambda from there, and we obtain here the beautiful number, and this number is 14.166. That number over there has a physical meaning. Lambda is what we call in power system economic the incremental cost, operating cost of the generation units. I will not go in details over there because there are other videos where we cover the theory, but basically lambda is defining the cost per megawatt hour, okay, the incremental cost. We use the incremental cost in order to obtain the dispatch, because what we need to do is substitute lambda into those two equations over here, and substituting lambda in those two equations over there, we can obtain that the active power dispatch of generator 1 should be equal to 6.58, and the generator 2 dispatch should be 3.41 megawatts, okay? Those numbers over there represent the active power dispatch of those generators. You can verify by hand that PG1 plus PG2 is equal to 10. That means that satisfies the identity constraint, okay? But now, what I want to tell you to the owner of this power system is the cost. How much will cost me to run this power system? And it's very simple, because I have two generation units. I know the two equations defining the cost, the operating cost, the production cost. And if I put here PG1 and PG2, voila, we have a total operating cost of 76.99 monetary units per hour, okay? What I'm telling you is if we are in the US, it will be 66.99 US dollars per hour. That means if this load of 10 megawatts is sustained by 1 hour, and I use the optimal dispatch 6.5 and 3.1, well, this will cost me 76.99 US dollar to operate, okay? Well, again, this has been a very simple and very interesting video regarding economic dispatch. The idea of this very specific video is to show you how to use the mathematics and obtain the operating cost of the electrical power system. However, I am doing this video because in the next couple videos, I will go to use some software to solve the same problem. In this very specific video, we use classical and basic equations, paper and pen, and we solve the problem. But now what I will do, thanks to Linem, my teaching assistant, that he pushed me to do something more and more interesting, we are trying to solve this. Where we are not trying, we will do this, we will solve this using 2 additional software, okay? Please stay in touch, keep watching the videos. If you like the videos, please feel free to subscribe to the YouTube channel. And also, if you have any comments or any question, please feel free to drop them at the area below for comments. Thank you very much for watching, and I will see you at the next video. And now I must say bye.